All right, ladies and gentlemen, hello, hello. My name is François and Etienne.
Hi.
Today we're going to speak about a crazy project we did with MEC Innovation Lab. So I'm leading the service innovation in 5G MEC. Basically, we are doing a lot of stuff with drones, holograms, and remote control robots. And this was kind of a novel way to showcase what 5G can do, AI combined on a MEC stack. And we'll speak a bit about all these things in a few seconds. So the idea was to recreate a bit the Mario Kart Nintendo Wii. It's a mix of a game and a live feed. I don't know if anyone knows this game or saw it. So basically it was, how can we reproduce exactly this, but coast to coast? So someone in Vancouver can drive a car in Montreal through 5G. So that was the spirit of the feature. And basically, we did just that for the Formula One. So Bell has sponsored the Formula One Grand Prix in Montreal, and it was a nice team to showcase this. I have a quick recap video that speak about it. It's only 1 or 2 minutes, but I think it showcased very well the project itself. It's in French, so it's also like a French immersion class now. So bear with me. Here's the results.
Aujourd'hui, c'est l'inauguration de la course belge, qui est un projet d'innovation qui a été bâti par nos ingénieurs chez Bell Canada.
C'est une expérience unique en son genre à la croisée du chemin entre le jeu vidéo et la course réelle.
Dans ce cas-ci, c'est de te faire courser une petite voiture de ton téléphone mobile à distance. Tu vas directement à l'intérieur de la voiture et tu courses comme un jeu vidéo.
La piste de course est installée chez Bell au centre-ville de Montréal et les participants peuvent jouer directement du Grand Prix à différentes stations qu'on a sur le site.
Donc, on se sert du Grand Prix du Canada, si vous voulez, pour pouvoir montrer ce qu'on peut faire avec la 5e génération téléphonique. Mais l'autre chose qu'on démontre, c'est l'intelligence artificielle. On est capable de suivre le téléphone qui est dans le véhicule par un contrôleur, ramène les données à un ordinateur hyper puissant qui prend des décisions rapides.
Le monde des télécommunications change de façon exponentielle. Ce qui était à l'époque transmettre la voix est devenu transmettre l'image. Maintenant, développer des applications en réseau. C'est 1001 applications industrielles qui pourront faire la différence dans la vie des entreprises, dans la vie des industries, dans la vie des gens.
Il n'y a plus de limite à ce qu'on est capable de faire. Quand on est capable de prendre contrôle d'un robot à distance, de voir ce qu'il fait, d'avoir les informations, les flux de la télémétrie et de le contrôler, on est en réalité en train de créer un nouveau marché.
On veut montrer la vraie face de ce qui s'en vient. Ça nous permet aussi de dérisquer les cas de figure potentiels qu'on veut vendre à des clients entreprises. Donc, si quelqu'un veut avoir une solution minière, d'agriculture, des choses qui veulent contrôler à distance par le biais d'un réseau privé 5G autonome, ou encore par le biais de robotique, on peut assister à ça parce qu'on connaît, on bâtit l'expérience à l'interne là-dessus. On est très content aussi de pouvoir amener nos équipes techniques, faire vivre à des clients l'expérience que la 5G va pouvoir offrir dans quelques années. Nous, c'est du concret, c'est du réel, on a du monde qui travaille là-dessus. On est très cher là-dessus.
All right. So hopefully you guys understood some of it, but basically it's just the image showcase of it, the track that has been created, the car that has been remotely controlled. So what's behind the hood on this one? On the left side, we have the mobile application, which is actually a web client. The goal was that we don't want to have a native application for the user. The main reason was we expected that the public will walk in, just kind of QR code, no installation required. In the end, we had a bit more challenging time to deliver this in 4 months. So we end up with only a web clients and with chosen phones. That being said, it's on WebRTC. It's going to connect to another phone, which is in the car. I brought one of the chassis here from the experience. As you can see, there's a Samsung flip phone. The reason we pick a flip phone is that you see the space is almost half. So we don't want a bulky phones on top of the car. The reason we use an Android phone here is really mainly that there's a super good camera, there's good processing power, there's a 5G modem. Everything was packaged in a neat little thing. We could have redo it with all the different parts, assembled it, make an integration, but it would have taken much more time. So this was a huge shortcut to take Android native development for the car itself using USB connectivity to a ESP32. So that's the ESP32. It's a $7 PCB board with I/O pin up that you can control it, remote control the electronics. So that was the bulk of it, and we use WebRTC in between the client on the web and the native application here to send telemetry and also receive the video feedback live from the phone. So that's the gist of it. On the support stack, we have the cloud. We have two types of clouds. There's the regular cloud for the web experience, so just regular web hosting. But also we've put a turn server on a MEC server. A MEC server is basically, I have a slide for that later on, obviously. And we also have an AI that oversees the whole track, so we can keep score and who's cheating and not. I have a slide as well on that. So that was the plan. First, we received the track delivery late in May. The event is in June. That was not giving us a lot of time to train an AI to track the cars and all that. So we had to rely on digital twins to train our solution. But as you can see, those are the render of the 3D artist that envisioned the racetrack. And this is the actual real track in the end. So it was not that far from the, there's a bit less this decoration, but I mean, it was not that far from the initial plans. Also, I don't know who's here familiar with 5G, except the buzzword 5G? You are? Okay. So in the telco stack, initially I thought it was just a fancy Wi-Fi, private 5G. In this case, we use private 5G. The reason we use private 5G, not the public 5G, the F1 event is like a super massive, dense amount of people in a small little island. So we were afraid of the disruption that might arrive potentially. And we're not owning the RAN on the island, so we didn't have the control over making sure the quality of the services would be ensured. So for that reason, we were owner of a N38 band within the island, so we use that band to put our private 5G deployment. And what it's kind of a bit more like a regular deployment of public Wi-Fi. Sorry, I'm just gonna. All right, so we do have like a core. This is the NDAC core from Nokia. It was a sponsorship from them, and basically this will handle the connectivity when you have a SIM card and say, hey, yeah, this guy paid his account, you should give him signal. It's a private 5G SA, so it was kind of novel to use this at the time. So it means standalone, so there's no piggyback on the regular 4G network to make that initial handshake. We have the radio and the antenna for the N38. N38 is not a really used spectrum in America. It's mostly used in Europe. We use it really for other stuff than the regular phone because it's not the best quality spectrum for high bandwidth, high throughput, but it was perfect for this stunt. So we had a little Raspberry Pi with a 5G modem just to test our setup, and that was the overall what we did deploy is these two pieces there. We deployed it on the track itself near the boot to get that private 5G signal so that the end user that will use our phone, special phone that support N38, not all the phones support them, would have a super good throughput 5G dedicated only for this experience. So that's the setup for the private 5G. And for the AI piece, that's also pretty interesting is that basically we had multiple camera across the track. This is our digital twins. So as you can see, it's based in Unity game engine, and we received the 3D models from the artist that made the car. And basically we trained using Unity. We generated a little AI that was trying to aim some nodes. Because if we were about to train an AI that always see the same playback track, it will not have trained with the randomness that we need for a real race condition. So we had to train a little AI that will drive the car across in a random fashion, a bit like the end user. And the beauty of using a digital twin for this was allowing us to label those pictures without manual intervention. So since we knew in 3D space where those cars are, we were able to generate the labels, the square there, and train a huge data set so that the YOLO pieces, I don't know if you guys are familiar with AI, but YOLO is a classification AI that allow, you send them a bunch of pictures with labels and position, and you say, this is a car. This is, in this case, we say, this is the blue car, this is the red car, this is the orange car. And after a while of training, it will know, no matter where the car is on the track, it will know what's the car, which type of car it is. The goal of that was to make a little mini-map, like Mario Kart, you see where the competitors are, but also, as we can see, someone trying to cheat on the grass, we can deduct points. Because if you're taking the grass a shortcut, we want to deduct points. And the real reason behind that is just to showcase that if we hook an AI inference near the edge, so in this case in the MEC stack, we have a super low latency that allow us to very near real time interact with asset in the space. So in the real life, what we hope to do is to make let's say a forklift is moving in a warehouse and we have that AI piece running in the edge, and we can maybe prevent accident or remote control robots with a loop of all the cameras in the warehouse. So this is a kind of a proof of concept we try to establish here. Also, the ultimate goal would be to take the actual feed from the phone, make it AI for self-driving purpose. So we didn't have time to complete that. We're still trying to do it. But basically what will be neat is that at the end of the race, when all the users are being disconnected, instead of bringing back those cars at the starting line manually, we would have the AI drive them back at the starting line. So we save a bit of a manual labor on that. So we're doing it we're trying to do it at the moment. All right, so the MEC stack is basically regular cloud on, let's say, GCP console. When you spawn a VM, is using the internet to get access to the cloud. The big issue with that is that if there's congestion here, you don't specifically know the quality of service you're going to get from the internet. So the latency to get from the client device to the regular cloud is a bit unknown. If there's a bad signal or if there's a lot of user using the resources, you might have an impact. So when we try to do real-time control of assets, that might be a big issue. So what we do with MEC is we install the same type of cloud resources, but on the telco stack. So the idea is that the mobile device get the radio antenna from the radio with fiber optic directly to the MEC stack and go back to the device. So this is only a 2 millisecond short loop versus this is variables and we don't know what's going to be. So it's much longer than 2 milliseconds in the end. So that's the beauty of MEC. There's a premium. Obviously, it's a bit more expensive to use these cloud resources because they are more narrow usage, but it's bring you that performance that might be interesting for gaming or real-time use cases that it's important for a specific customer. So hope you learned something here on MEC. Not sure a lot of people knows about that, but it's now a feature. On AWS, it's called Wavelength. On the MEC stack for Google, it's called GDCE. So if you have questions on that, I'll be gladly answering that. And I'm about to shut up, but this is like the evolution of this prototype. So before we go with a full RC car that cost near $600, we had to experiment and prove that 5G is indeed able to remote control robots. So we made some early prototype with this Amazon bot here that is $75. I think Etienne also brought the Google robot kit that from other GDC event.
Yeah, GDG indeed. Yeah.
So basically, you can see the evolution to finally arrive to this spot where we have our custom 3D printed thingy and the don't close the phone, don't folder 3D printed. And these things can go pretty fast. It's 70, I think, kilometers per hour that can go at peak speed. We had to reduce it a lot because otherwise people would just crash them at super high speed in the track itself. So we fine-tune a bit the speed and all that, but it's we still have a wish list to go on the actual race circuit and go full speed on the Grand Prix next summer. So early mock-ups of the design. what's the finish with the casing? Sorry, I didn't bought the casing. It's kind of fragile, so and you can see initially we had that windshield, but it made some weird glare and plastic. So we at some point we just remove it with a with a cutter.
Tell them how expensive they were.
Oh yeah, no, these are custom mold. So I don't know if you're in the mold business, but it's super expensive to do, like crazy expensive. So they had to like a CNC, a block of metal, and then it's the same thing that you get for packaging. So when you know the annoying packaging, transparent packaging, it's the same thing. It's being painted on top, but this is the plastic used for the mold itself, and then it's spray paint and vinyl and all that. But yeah, so we can technically print out 1,000 of them if we want, because we now have the mold. But the Walrus is the company that made this for us, and it's anyway, it was kind of a pain to get, and it also brought lots of delay on delivery for training on the real asset on the racetrack for the AI piece. The beauty is that if you have to train AI and you might not have a real scenario, digital twins is the way to go. It allows us to train, and the models that we train with the digital twins versus the real feed from the camera was almost a perfect match. So of course, there's some glare, some little issue that has to be fine-tuned, but it was very up to 85% accuracy just based with the initial training on digital twins. So yeah, the experience is, initially we wanted the whole public to be joining from all over Canada. In the end, with the time, it was more like, okay, let's just do the F1 booth, and we'll be fine. So maybe next year everyone will be able to join. Honestly, we won't organize a race today because the people on the weekends some of them are not working. So basically, but it's more fun than just a virtual racing, because you feel the physical aspect of the race itself. I didn't saw. I was there for the 3 full days of the activation. I saw only smile, only people having a lot of fun, much more than any race games that would have occurs. Because the aspect of binding reality for a live feed really brings some level of magic that is an edge, I would say, on the experience itself. So maybe one day Bell will say, okay, you know what? Let's do it a full year. Let's organize some races and do something on it. We'll see. All right. So the live demo, Etienne?
Yes, the live demo is not going to happen right now. So
unless you have a long nose cutters.
Yeah, but what we will do is I will show off a little bit what the different interfaces look like and the pieces that we have in front of us, just for a second. And then I'm going to talk about the actual tech stack. The other thing we do intend to do, so as you can guess, there's a lot of really finicky bits in all these kind of prototype projects, and we've run into basically every single one of them. So we had 3 different prototype cars that we brought today, thinking, with this, we can't mess it up, right? So the first one, I spent late last night trying to crimp new wires and getting it all ready for today, even got this little shoe-mounted thing, only to have all the pins rip out just before I came in during transport. This puppy right here might save us a bit later today. We want to do is to get it to run and demo it for you in the lobby. And this right here ran into the typical, I'm on a university Wi-Fi and people are really serious about security, and so the WebRTC is not cooperating with this setup. We do have fallbacks, which we hope will get to work a bit later today, so we'll have the live demos. If after the talk, if you're curious, I invite you to come up, look at the cars, ask us questions about any of the details that we might not have covered in the talk. And what I would like to do is to demo, you know what, I'm looking at time, I'm wondering if I shouldn't just jump into the talk and then demo the actual UIs for the web later.
You're the boss.
I think I'm going to do that. So we'll see how much time we have at the end, and we'll do a bit more of an impromptu thing where I'll disconnect this laptop, I'll connect mine, and we'll just look at the UI and I'll answer questions live here. Since we're not 100 people in this room, we'll be able to get a bit more up close and personal on this. So the tech stack. How did this project go about? The thing is, we made a few choices when we saw the time we had in front of us. So this kicked off last January. Our small but mighty team, just basically kicked things off, and we were 4. And we had a deadline of mid-May, officially. Just try not to, make the deadline right up to the race, because who knows what could happen and, put us right up to that deadline and be all stressed out and stuff. But one thing that we did want to do is to de-risk the project. So the main team that was going to do a lot of the website with like the actual on-site track and was going to do all the dressing on the website and reuse the different tech stacks that we had, that main team was not going to start really working in earnest until mid-April, as the original plans were going. So what we wanted to do at Bell, I'm a contract worker for Bell, but our team at Bell was trying to de-risk the whole project, build a proof of concept prototype. And so we knew we wanted to have a web component to this solution and an actual onboard device native component that would control the cars. So we picked Kotlin as a technology, Kotlin multi-platform. This allowed us to have effectively a common store of code that would handle all the different connection and the different signaling that WebRTC peer-to-peer communication require. While both targeting the web and native Android, we could write most of our logic in this sort of common Kotlin code and have like the front ends be the only distinguishing parts. So that in fact helped us save a ton of time. So while we were evaluating this project, what helped us along and sort of made us also pick Kotlin multi-platform was this great little library called appropriately enough WebRTC KMP. So this brings you iOS, Android, and the web all under the same roof. It has also a lot of nice little benefits I'm going to talk about now. So the thing is that this library sits as an abstraction layer on top of both native WebRTC libraries and the web stack that you would get out of Chrome or any browser on a mobile device. So for iOS and Android, with this library, you can target basically everything. And under the KMP library, you can pick and choose which actual binaries that you want to use. So when we started out, this library was using this project, the WebRTC builds from the React Native folks. So the thing you need to understand about WebRTC is that at the core, it's a Google project. At least most of the native implementations that you're going to see out there are coming from this website, this project. So that's the WebRTC org. And they don't necessarily take care of shipping binaries for all the different platforms like Maven or all the repos that you might be used to as a developer. So the thing is that that's kind of tricky because you end up with a lot of different builds out there, right? Like we just mentioned the WebRTC one from the React Native folks, but there's a few others out there. So I'm going to talk about those in a sec. But what I should mention about the Google org site is that while it has usually not been updated a whole lot, they do accept community offers and community help. So this website you see here is actually super nice, very well done, and it's done by a friend of ours called Eric Hallman, who also helped us on this project. He's a well-known figure in the Android development community. We reached out when we wanted to accelerate our flow and really keep our latency at a minimum, razor-thin edges of performance we had to go get in there to get the proper reaction out of the cars. So I just put that slide there to both say, this is his handiwork. There's a lot to learn here. I encourage you to visit this if you want to really do the whole tutorial chain about WebRTC and get deep in there. And the reason it's nice is because he basically updated it. So given that Google doesn't very often update their own libraries, this library here, the WebRTC KMP library, from the folks at LiveKit and the Flutter development community. This is the new one that's being used for the library that we are using underneath the hood. So the big benefit here about the KMP library concept is that you can swap out the native libraries whenever you want to get better support, because if you know a little bit about native development, it's not a trivial space to be in, right? Like you need a certain amount of resources to be able to develop these kind of libraries and see and make sure that they work well on all the different devices out there, right? So to be able to have hot swappable native libs is basically really a godsend. So yeah, just more different libraries. If ever you're curious to look at the slide, I think you'll be able to see them from the video, the different links to the different stacks out there. There's a lot of nice little details that you can go dig into if you're into that sort of stuff. So anyway, while the WebRTC internals, we can delve deep in there and get super intricate and really in the weeds. I'm going to do my best, no promises, to not rabbit hole today. I'm going to try to touch on the big principles that you would need to sort of understand about WebRTC to find your way in that landscape. And so, as I mentioned, our project, one of the big advantages we had is that we had this lib shared module where all the common code was sitting. And so most of what I'm going to talk about today in our project is common code. So most of the logic for establishing connections and signaling between peers and setting up all these streams is common code. Now you have three big components to WebRTC that you need to sort of think about whenever you work with it. The media stream side of things is where you connect to whatever device you're running on, be it a web browser on your laptop or on your phone or a native application on the device. You need to have access to the camera. So the media stream part of WebRTC is what gives you this sort of common API to query the system about what kind of cameras do I have, what kind of frame rates can I get, what kind of resolutions can I expect from this thing. And once you poke at these APIs, they can give you objects that you can then pass on to the RTC peer connection layers and the RTC to sort of start establishing connections and advertising what it is that you're going to offer over this connection. So one of the big things we had to mess a lot with during this project with the cars is to effectively ask the camera of all the different types of phones, okay, so what kind of frequency can you give me? What kind of resolutions can you hit? And that might sound simple, but a lot of the different cameras in there don't offer the same capabilities depending on if you're using the macro lens, the close-up lens, the selfie camera. Some of them have stabilization, some of them don't. Some of them can offer you super high frame rates. Others can only offer you like very low frame rates. And you sort of need to strike the sweet spot where you're able to say, okay, well, if I'm picking this sort of mid-tier resolution at a good frame rate, what kind of streaming am I going to get out of it? What kind of bandwidth am I going to need to have like a very responsive experience? Anywho, the idea is that you take all the media stream info, you make your picks, you pick your poison, you then pass all that along to an RTC peer connection module in WebRTC, and that one is where on both sides of the communication, both devices will configure whatever they're offering or not. You can be part of a WebRTC connection and offer no video whatsoever, only audio or nothing. You can also decide that your WebRTC connection is going to be, I'm getting video and a data channel from this end, and only video and only a data channel from the other end. So you can sort of mix and match as you want. And the data channel I touched on is how with those cars we managed to control the actual devices. So what we do is that when we get telemetry from be it the controller or the game screens, what we do is whenever a user presses a button or sends information, we send that as a pure byte stream through the RTC data channel. We don't need to establish a separate WebSocket connection or mess about with that. Once you establish a WebRTC connection, you get both audio, video, and the data channel that's allowable. That's really useful in this case in this project. All right, so we're okay on time, but I'm going to try not to bore everybody. Like, who here is actually an Android developer? Like, so we have a few people that will be, used to all this crap. Who here is more like from the back end or the website of things? And yeah, cool. So yeah, you'll be interested more about maybe the communication between the different peers. But anyway, like to keep it sort of simple, this is the typical code that you would get to sort of define your full WebRTC connection on either side of the connection. So the big components are here. You have those media streams that I talked about. So you have this concept that you have a local and a remote one, right? You're working with the same objects on either side of the peer to sort of grab your video frames, grab your audio, and so on. The current peer connection is, as you would expect, what describes who am I connected with, how's this connection going, are things good, what are the kind of stats that I'm getting over this wire, so that's that kind of stuff. Then we have data channels. As sort of the structure indicates a little bit, you will have effectively like how many data channels, however many data channels you want, and since they're, how to put it, very configurable, you can decide to effectively send whatever you want on these. So to give you a hint, if, for example, you're working with cars like these, right? We're sending controls over the wire, and we have a joystick or a phone with like a joystick-like interface on it, and we're sending these controls. That stream of data, you can't just expect that every little pieces of information, right? Like, okay, my sticks are like this, my sticks are like that. They're not all going to make it to the other side of the device in time, right? This is the internet. Some packets are slower than others. So when you're establishing these connections, you have the choice to say, I actually don't want to, I don't want the TCP/IP proper stack to get everything in order and make sure that all the deliveries happen and have a retry. No, you want it to as fast as possible and the latest one. So you can configure these channels to basically say, look, give me what you have, give me the latest. I don't really care about timestamps. I'm just going to get it, and if it's too late, just drop it. Right? So you can configure these data channels to behave as you need them for your application. And the current RTC session job, well, actually I'm going to talk about it just 1 second, is this concept, which is kind of fun with Kotlin, that, well, how to put it, WebRTC connections and setups and all that are not that complex, but where you hit the wall a little bit when you work with these things is handling proper closure and opening of all the resources, the kind of threading that you need to receive all this. This is effectively really tricky. If I'm honest, it's really the more difficult part of this whole project. To close everything in time, to make everything just right. Because trust me, the WebRTC stack, if you do not do things in the right order, it will kill you. Like the process will crash, the runtime, and it'll crash at the native level, so you're in trouble. So you need to cross those T's and dot those I's just so, right? Anyhow, so the idea of the job right here is like a coroutine job in Kotlin. If you're not familiar with coroutines in Kotlin, they're like a very nice way of handling what would have been threading in Java and a bit of a mess. With Kotlin, coroutines afford us sort of a way to control the different jobs and different processes in a way that's very natural and not think about them too much at every separate part of the app. You just basically launch jobs. You make sure that there's a parent job somewhere, which this is, that you can shut down cleanly. And if you've done your work right, everything else will go along with it. Right. So, like I'm looking at time again. So very quickly, this idea is like, this is how you grab the different media information from the system when you're working with WebRTC. Yeah, I'm going to skip a little bit. We get the idea, right? I've talked already about like resolution and how to get FPS. So you effectively tell the system, this is what I'd like to get. And then depending on where you're calling from, right? Depending if you're on the web or if you're on native, you're going to get what you want or something close to it. So if you're on Android native, you tend to be able to look at the actual precise list of the different resolutions that are afforded to you. If you're on the web, it's a bit more fuzzy. Still works, but you can sort of say how, like by using the ideal function right here, I'm basically telling the system, look, I really want this resolution. Whereas if you're not as picky and you're, say, on the client side that's controlling the car and you're just like, okay, you know what? Just pick something that's decent between this and that. You can sort of specify to the system looser requirements. And yeah, this on Android, this is the way that you would specify which camera you want, which is super important in the case of the car, which is why I put that there. Right? You want to be able to say, I want the wide-angle camera that makes it look like I'm actually sitting in the car, and not the other one that makes everything looks like I'm a toy or something. Yeah, that we'll just skip over. All right, so this slide here is more about how the connection establishes with a WebRTC setup. And so the idea is that effectively the phones here, like it doesn't actually matter all that much who's initiating things, but whenever you have a WebRTC connection that's setting up, one of the two parties is going to make an offer. It's going to basically say, okay, I've configured my things, I have my media, I know what I want, I kind of have an idea what type of pipes I want, I just want video and that's it. I'm going to offer up this sort of connection to somebody. I'm ready to accept anybody that wants to connect. And then in our case, the cars with their own WebRTC clients would answer to this, would send like an actual answer type class object instance that says, okay, cool, I'm interested. This is what I'm offering. These are the things I'm going to send you back. In this case, the car will send the video feed and a data channel No, the car doesn't send the data channel. It's the other way around. The car only really effectively sends video. That's that was an interesting little animation. I don't remember what that was about. Okay, so and then what happens after that? Once the two parties have basically said, okay, cool, this is what we want to do, we're ready to go. The two parties need to establish a connection, and that's where things get hairy, and sometimes, you know, we'll have a hard time resolving, a bit like what we had today when we tried to set up this morning. So the idea is that you're going to be sending different candidates, effectively packets of information that say, okay, I'm a thing on the network, I've talked to my server, there's a server in there somewhere in this story, which we'll get to a bit later, I think. But the concept being that you will need to advertise to your peer all the different ways that you think it could try to connect to you, effectively meaning the IP address. And what that allows you to do as two peers trying to connect on a really, you know, unknown internet is to say, I know I'm here on my local network, I know I'm visible as this on the internet, I know I'm... So you give out all the IP addresses that possibly could work effectively to connect, and you both share this list. And then you just start trying to call each other until the point where it either works or fails. And that typically will end up working. Like with WebRTC, you have different fallback mechanisms that allow you to go through all sorts of different networks, right up to the network where, you know, the system admins don't actually want you to do video calls and it will just not fail. Yeah, that's about the idea. Here, a little slide on the concept of the RTC model. This is more like what we just saw in diagrams, right? This idea of events. Some of them here are more like events I sort of created for my own stack. Like the thing you have to understand with WebRTC and sort of what this slide illustrates is that while you have a very precise protocol that you're supposed to call in very specific ways, the way that you signal and send out the candidates to each other is up to you. It's not WebRTC's responsibility. WebRTC just says, well, look, this is how we work as a protocol. You need to do these steps, and these two things are going to find a way to share candidates with each other. Otherwise, we can't even connect, right? So you're sort of responsible for that part, and you're also responsible for deciding when you call offer, when you send an answer, when you send over candidates, and so on, right? And the other objects that you see in this sort of event class, which represents different things that are going on between two peers, are more like things I decided as a developer I needed to sort of make sense of a WebRTC connection. So in my specific case, I had this idea that one of the parties initiates a connection and the other party expects somebody to call in. So this is just a way to, you know, sort of make sense of who's who and what role you're playing when you're establishing peer connections that are part of my little stack. I think close is, you know, fairly self-explanatory. Anywho, so this diagram sort of recaps again a bit what I've been saying. Same idea. Those candidates in proper WebRTC terms are called ICE candidates. Doesn't necessarily matter. We're running short on time, so this I think I'm not going to go through like the whole details of it, but effectively this is where, you know, like this is part of the code that sort of makes this signaling negotiation happen on our app. Again, the concept of how we store this information doesn't matter all that much. I'm going to talk about more fun stuff now than code. We have I have a bit of time, and I want to leave some time for answers, questions, and just actually looking at the hardware a little bit and showing you the different interfaces that we have set up. So WebRTC, super interesting technology. You know, maybe a bit long to talk about that for hours on end. So let's look at the hardware now. What kind of fantastical hardware do we need to get an Android phone hooked up to our little race cars and rovers and whatnot? So the ESP32, as François said, they actually usually cost like something like $7. Yeah, I did not update the
But that's the fancy one with the screen. So.
Yes, that's even more fancy. This thing has a screen. It's got like, it even has LoRa 32, which is a way where these things, even without a Wi-Fi, with a LoRa stack, which, well, you can see here, this little thing is an antenna, effectively, for the LoRa, this thing right here. So LoRa stands for low power, high range, versus Wi-Fi, which is like high power, low range, right? LoRa is really great for IoT type applications, which is clearly not what we needed for our own stack. What's interesting to think that for like something like $25 or whatever, you effectively can have a little microcontroller with a screen, and they could talk to each other independently, and we're talking like hundreds of meters, if not kilometers apart. And that's kind of bonkers for free, right? Which is maybe not something I should be saying while I'm presenting for Bell.
It's okay. Low bandwidth. We're high bandwidth.
Low bandwidth, that is right. Like you still need somebody with like a proper 5G network. Trust me, if you want to get something really hardcore running like those little cars. What's also nice about these ESP32s, and what they all have in common, is that they're very easily programmable and powerable just through a regular micro USB connector. This right there, what's that? Oh yeah, you have like stuff like power management. So with a tiny little LiPo cell, you can power a board like this for weeks on end, if not months on end. And it's able to run Wi-Fi, BLE, that low power, super high range communications I was talking about. And yeah, they're really incredible little things. They're super popular in the IoT community and the do-it-yourself community. So right here, for our rovers, we have a couple of different setups. So the rover, the main one, the proper one right here, has its own little power engine coming from the RC world to be able to effectively, propel this thing up to 75 kilometers an hour. These things are nuts, right? It has its own little battery. It has a nice little control system that goes with the motor. We didn't have that for our original prototypes. So what you're seeing here is the SP32 on the left, and on the right, you're seeing a motor hat. You need a motor hat to drive like regular little motors like the ones I have on the other rovers because they operate with pulse width modulation signals. So you just need to have something that can both send the right pulses in an easy way, but also power them the right way as well. Right? On this RC car right there, you connect a big battery directly to the motors. In our case, we needed to have two separate power paths to be able to drive the motors and to power the SP32 separately. So that little hat right there, what's kind of interesting is that it's originally built for a Raspberry Pi. If you look at the black connector where I have little wires sticking in, those boards are built to go on top of a Raspberry Pi and know what exactly the pinout of a Raspberry Pi is supposed to be, and you can easily program them that way. So I was able, with the ESP32s, to repurpose one of those and start talking to it from something that's definitely not a Raspberry Pi, right? Just by using the right pins and communicating with it. So that was kind of an interesting little hack that we did for our first prototypes. The first prototyping setup looked like this. So as you can see, we're trying things out, making sure that we can communicate between the phone and the device. The idea here is that the ESP32s are connected to the phones via a USB cable, simple USB cable, and the phones can talk to them as if they're just talking to any serial device. So you can open up a port onto the microcontroller with the Android app and just send bytes down the pipe. And once you've programmed the ESP32 correctly, all it's doing is reading for bytes, for, in this case, 4 bytes, which give it direction, power, direction, power. And what we've done with these little things is that we use them as tanks. So 2 sets of wheels on each side are programmed to go the same way at the same speed. So if you want to control them, you're basically like a tank would drive. You're telling it, give it power that way on this side, and you can pull back if you want to turn on the other side, or if you want to go forward, you just go 2 ways forward. So that's the big difference between a tracked device like that one and this RC car right here, which is propelled through the back and has a separate control line for the wheels up front that will tell it which way to go, right? So these are really different ways of processing. So at the end of the day, once everything is lined up and the wiring is super simple, the problem I had is that I needed this thing to be ready for the rigors of like the actual real world, right? So I needed to think of a nicer, tidier setup. What we did is pretty straightforward. We went with a 3D printed little mount that we set up on the rover, and we started making things a bit tidier and a bit tougher. One thing I did not plan for is the rigor of transporting this thing in a bag, which you can trust me on the next 3D printed design. I'm going to have little shields that are going to protect all the wiring because I broke all of those, as I was mentioning earlier when I came in today. Anywho, all right, so I'm going to go a bit faster through the slides here, but How do you program in ESP32? This might look a little bit intimidating, but for those of you who are old as me, this is C. This is plain old C. You can even do C++ in there, but...
Just ask ChatGPT. You know?
Yes, ChatGPT. ChatGPT is like the memory I did not know I had. I just asked him, how does this stuff work again? He was like, and you're like, okay, cool. But at the end of the day, like most of the programs that control the cars, I had not done C in like decades, literally. And I got around to fixing these up in less than a day. So this was the least challenging part of the whole project and the more entertaining one, if I'm honest. If you want to have a bit fancier of an IDE and you're going to get deep into the microelectronics world and the IoT programming, all that, Platform.io is something you want to keep in mind. That's an IDE that runs on top of Visual Studio, a plugin, if you will. And it provides like a ton of support for all sorts of devices. So once you are able to write a little C program on Platform.io, you'll be able to not only target ESP32s, Arduinos, all the other microcontrollers out there. The list is too long to even get into. If you want to control something like this, microcontrollers, any type of microcontrollers for any type of project from an Android device, this is really, so far, the best library I've seen. I looked recently to see if anything new has come up. Not really. So Mikey's USB serial for Android, it just exposes serial ports, but you can also access other types of USB devices that would be connected to your phone. So that's a nice library if you want to mess around with like DIY projects like ours. This slide was also, I already touched on this, but the idea that the ESP32 is so cheap and cheerful and easy to program, it didn't matter when we needed to switch from a tracked control system to the RC cars right here, which are like slightly different. We just needed to swap a few bytes around, make sure the protocol made sense for what we sent over, and we were done. So nothing really difficult. The ESP32s are really well suited for that type of application. Really lovely little things. All right, so I'm gonna end with like a little, demo reel of all the...
Not the same.
Not the same one, just like the quick and cheerful, what does this look like and what was the experience like for people who tried it while it was still set up at Bell Media. It's a lot less exciting outside the car than inside the car.
On the phone, we play fake sound of F1 cars, so it's more immersive. Those cars doesn't make those sense, obviously.
Yeah, and that's basically it for us. Thank you.